All
Yeah.
right. Well, as he said, welcome back from lunch. If you are looking for performance-driven development by Jim or doing bad things with APIs with Tim, you are in the wrong place. If you're looking for Lambda on, well, PHP on Lambda, then you are in the right place. I am Ian Littman, and, well, you can follow along with the link shown on the slides. You can follow me on socials as shown on the slides. Other than that, let's get right into it. So, in this talk, we'll go over a little bit about why you would potentially want to use Lambda in a couple of cases where it's like, okay, well, there's performance implications of what you do on Lambda. There are billing implications of what you can do on Lambda, and you still might want to use it. And the thing is that Lambda doesn't have a PHP runtime built in, so you kind of have to bring your own. And we'll walk through how exactly to do that, starting from kind of the ground up. And we'll see how that works in a couple of contexts. One is responding to events asynchronously, basically responding to an email with another email, and kind of utilizing this stuff that a few of the 300 plus or 200 plus services that AWS provides. And we'll also see Lambda operating in an API context with both API gateway and function URLs, which is simpler than API gateway and costs less money and has some limitations, but you may not care about those limitations. In addition, we'll talk a little bit about the new container image support within Lambda if you need to do something a little bit heavier, and depending on time, we'll touch on Bref. Okay, realistically, we'll touch on Bref anyway because it's super quick to get started, and that's what you should be using in production rather than the things that I'll be walking you through. I'll show you the hard way, and then Bref can be the easy way. It involves NPM, though, but we'll forgive Matthew for that. So with all of that, there will be a fair number of demos toward the end of this presentation, and hopefully the Wi-Fi stays good enough that I can upload a 5.5 meg file. So without further ado, there are a few things we will not cover. For example, fully automating things outside the context of Bref. We're not going to do AWS SAM, which is the way to kind of run serverless functions locally for testing. We aren't going to deal with Laravel Vapor. A few other items here that, for the sake of time, we won't touch. So, the thing with Lambda is there are no servers to worry about. There's no container runtime to worry about unless you really want to worry about that with a Docker image. You just upload your code, and it just runs. And it just runs in a way that is billed on a very fine-grained basis. It's actually billed per millisecond here. The last time I did a version of this talk in 2020, it was billed per 100 milliseconds, and now it's a lot more fine-grained. And each execution is shared nothing-ish. We'll get into the caveats there in a moment, and we can use those caveats to our advantage. But you can scale out from 0 all the way to 1,000 or to potentially more concurrent invocations of whatever your code is. And you don't have to worry about auto-scaling or the amount of time that it takes to do that. Your functions, little bits of code, scale in a matter of hundreds of milliseconds. So this is made possible by something called the Firecracker micro VM that AWS built a while back and now uses both in Lambda and in their serverless container service, Fargate. So this is all well and good, and also on top of the scaling benefits that you have with Lambda rather than trying to scale up and down servers that scale on the order of minutes rather than hundreds of milliseconds, you have the ability to integrate with various AWS services which AWS uses to a fault. In a lot of blog posts, they'll say, hey, here's this simple thing that you can do with only 25 easy steps involving 3 Lambda functions, step functions, an API, gateway, or 3, and 4 or 5 other services. Lambda tends to be at the heart of a lot of those posts because you can listen to events from various sources and react to them either synchronously or asynchronously. So as an example of those interactions, you can watch for files to be added to S3, which is what we will actually demo later on in this presentation. You can listen for notifications on a simple notification service. You can watch for messages in simple queue servers, or SQS, either individually or batch. There are a few ways of handling things there. So you can have a queue worker set up that, that scales so rapidly that either you don't really have a queue backlog to speak of, or you bring the services down that don't have very high level of quick scalability. One of the two. Now, if you want to serve HTTP requests with Lambda, then it's honestly a little bit more involved than it should be, but as time has gone on, they've made it easier. There are really 3 different ways of serving HTTP traffic onto a Lambda. One is via the application load balancer, the thing that costs you roughly $25 a month, plus traffic and such. And you can set endpoints on the ALB to route to Lambda functions. Alternately, you can set up an API gateway and map routes to Lambda invocations. Finally, and this is a relatively new addition to Lambda, there's something called function URLs, which expose, using the same event format as an API gateway, they expose your Lambda functions directly as, well, URLs. And you can either not authenticate them at all, or you can use AWS's IAM system and permissioning to authenticate, which I'll mention a little more detail later. Finally, if you don't need to call something over HTTP, you can use AWS's API to pass data to Lambda directly. They have an API for Lambda invocations as well. So plenty of ways to call Lambda. Again, there are a number more of these, and as you'll see later in the demo, there's a big long list of event sources that you can tell Lambda to react to. So I said shared nothing-ish. That's because Lambda actually keeps your little function invocation around, or sorry, function instance around across multiple calls, what Lambda terms as invocations. They have a bootstrap phase, or cold start, where things get set up, and then they'll run requests through until you either have an extended period where you just don't need that level of concurrency, or something fails, or you time out. Now, you can set that timeout. This is within the execution of a function, so you can set that timeout up to 15 minutes. If you're serving a web request, obviously, it's going to time out well before then. If you're running some sort of batch processing job, you might run up against that 15-minute limit, at which point Lambda will say, well, this execution context has gone off the rails. We're going to shut it down. Anyway, the containers get kept around a bit so that they can respond more quickly to requests as they come in, because there is some level of overhead measured in hundreds of milliseconds, or maybe 100 milliseconds, depending on what kind of code and how much code you're running, to get that Lambda started from scratch. Now, once that particular instance of Lambda gets set up, it has access to /temp. By default, that's a 512 meg partition, so if you need to cache data quickly, locally realizing that that cache is not going to be available to any other concurrent execution of Lambda, you can throw it in /temp, and 512 meg of /temp is free, and you can get up to 10 gigabytes of cache in /temp if you are willing to pay for it. So in addition to that, you can persist state to, of course, S3 or a database like Dynamo or MySQL or what have you. Or you can attach Lambda to the Elastic file system, which unfortunately is rather slow, so you want to use that carefully. So there's this concept of invocations versus instances. An invocation is a processing of a single event that is provided to a particular Lambda runtime. And you can have multiple of those invocations back to back to back over the lifetime of a given Lambda instance, effectively a VM or a container, as you will. So what this does is, again, it allows you to run a little bit more quickly than if you had to build every single thing from scratch every single time. Now, one thing that Lambda does not do is, per each instance, process multiple requests concurrently. So if you have 10 web requests coming in at the same time and you're using Lambda in that context, then Amazon is going to spin up 10 instances of that Lambda function. Those are going to have each their own /temp, and each one of them will have its own little sandbox to execute based on that request. So it is shared nothing when you're doing multiple things at a time. So instances are different than invocations. Instances, simultaneous instances, are where you get your concurrency. Unlike things like Google Cloud Run, where you can throw multiple concurrent requests at a single container, on Lambda, it is one at a time per instance. So a couple more items on performance. Historically, the amount of RAM that you could throw at Lambda was between 128 meg and a little under 3 gigabytes. Relatively recently, they increased that maximum amount to 10 gig. So if you have some really heavy, crufty script, then you can throw it in there and it'll still work. As you scale up RAM, they give you a proportional-ish amount of CPU. 128 meg does not give you much CPU, and it actually throttles your CPU time down, so functions will run more slowly at 128 meg than at 512, a gig, or roughly 1.8 gig is where you get a full core of CPU time all to yourself. Given that we're talking about PHP here, one core is all you're ever going to need on Lambda because, as mentioned earlier, you're only processing one request in a Lambda instance at the same time. You're not going to get performance impact above that, so basically don't bother with something larger than 1.8 gigs unless your script just is super memory hungry. To that end, Bref and serverless framework in general have a default of a gigabyte of memory allocated to the function, which gives you the lion's share of a single core, and that's usually enough to have a proper price performance benefit because the amount of CPU time that you get and the amount of money that you pay both scale linearly with the amount of RAM that you allocate times the amount of time that you keep the function running. Now, that also means that there is kind of an optimal bit where your function runs quicker the more power you give it, which means that it takes less build time, which means that by throwing more resources, you may actually end up with your function costing less. So, and again, with that 10 gigs of RAM, you can have up to 6 cores, although, again, you were talking PHP, so you're not going to do anything useful with them. There are a few other limitations that are here. If you pull a copy of my slides, that is linked, and that'll take you to the AWS page where it goes into detail on a few other limitations that you may or may not have any likelihood of hitting. So, as mentioned on the billing side, you're billed on gigs of RAM per second at 1 millisecond granularity, which means that like there used to be 100 millisecond granularity that would mean like, okay, make sure that you don't have a function that runs on average for 201 milliseconds because that's going to cost you 50% more than one that ran for 199. That's no longer really an issue. It's super fine-grained. But if you throw more resources at a function and it runs proportionally faster, then your end users get a better experience, and you wind up paying the same or less. Now, billing includes execution time even if the CPU isn't doing anything. So if you have a Lambda function that is sitting there and calling an API that takes 10 seconds to return, congratulations, you just spent 10 seconds worth of Lambda billing time and have maybe a web response to show for it. So for things that are very IO weight driven, particularly operating over HTTP, Lambda, particularly if you have a kind of consistent level of scale, may not be the most cost-effective thing out there. Like the prices aren't horrible, but if you have consistent load and are waiting around for I/O a lot, then it may not be the greatest use of your money. So another bit here is relatively recently Lambda added support for ARM CPUs as well as x86, which is what they've had from the beginning. The ARM architecture, similar to the machine that's sitting in front of me, does require binaries to be recompiled for that architecture in order to work. If you get the recompilation done, which PHP runs perfectly happily on ARM, then you get, I believe, a little bit less performance versus the x86 instances, but also things cost, I want to say, about 16 or 17% less. So you've got an option there, and if you wanted to, for example, build something locally and compile something locally on your Apple Silicon Mac and actually have it work on Lambda, that's fine. You can totally do that. They support ARM there too. Another note here, there are two stages, the cold start initialization phase and the warm start and execution phase. In the case that we're talking about for custom runtimes, which is what you'll need to use with PHP, you are billed for both. But based on the latest that I've read, you do get a bit more CPU during the initialization phase than you do during execution. So initialization phase, at least historically, you'd get 2 cores even if you only have 128 meg RAM. So if you want to do some heavier work on the Bootstrap side of things, then you'll get a little bit more compute there, even if you spec things down later on. So one thing with Lambda is Virtual Private Cloud, or VPC, has some limitations. Now, of course, you need Virtual Private Cloud and you need your Lambdas inside of that when they need to reach out to some piece of your infrastructure that is also VPC only. So that might be your database, that might be Redis, something to that effect. The limitations there are, unless you have a NAT gateway which costs 5 cents per gigabyte and 5 cents per hour, even in the London region, they bill it in US dollars. You have to have that set up in order to cleanly get access to the internet from your Lambda within a VPC. If all that you do within that Lambda is contacting things that can be reached within the VPC. You don't need the NAT gateway. So what you can do architecturally, if you need stuff in a VPC and the cost of outbound transfer is an issue because you weren't planning on setting up a NAT gateway and having it sit there and bill you for your serverless thing. If you weren't planning on doing that, you can split your architecture to where anything that needs to contact internet-facing services is in a Lambda outside the VPC, and anything that requires connectivity within the VPC is split off, and you just have one function that's contacting internet-focused things and another that's not. Of course, you would then need to set up some way for those functions to talk together, so throwing things onto a queue or S3 or the like. So it's a question of, do you want to spend more dev time architecting that, or do you want to spend more money subsidizing Amazon.com? So one thing that used to be an issue with Lambda inside the VPC was cold start times. You would see 10, 15-second times to get a first function call running if the function had gone to sleep or hadn't been called to start with. That has not been an issue since 2019. Things are just as fast inside the VPC as they are outside. So I've kind of set the stage here, and we really haven't talked about PHP on Lambda other than saying you only need one core. So the way that PHP works on Lambda is you kind of have to bring your own runtime. Now, there are two ways to do this, and this presentation will primarily walk through the way that involves uploading a zip file with the basics and then uploading another zip file with your PHP code. That uploading the zip file with the basics is you take an Amazon Linux 2 instance, and then you compile your PHP runtime against that, and then all of your library files and binaries and such. You take those, you throw them into a zip file, and you upload that as what they call a Lambda layer, which again is just a file system that they drop in /opt. So when you define a Lambda function, you can say, hey, I'm going to cherry pick this layer and this other one and stack them in whichever order you want for that particular function. And then you have access to those files and thus that runtime on whatever function you're running. So by doing that, and by using the kind of Lambda custom runtime endpoints API that we'll go into in a second, you can actually run anything, whether that's a shell script or some esoteric language or PHP, within Lambda, and it will work. The other way is via Docker container images, and we will get into that in a minute. So one thing that is important to note here is Lambda does not speak HTTP. Lambda has its own event format because the way it was initially built was like, okay, well, we're going to have, something was uploaded to S3 and then we're going to act on it. So being event-based, you get this big blob of JSON back saying, hey, a photo or a file was just uploaded to S3. Here's what happened. Here is all the information that you need to maybe do something with that file. Now, there are events that represent an HTTP request, including headers and a body, etc. But those events are not standard HTTP messages. You don't go in and set up a PHP web server and then expect Lambda to send you HTTP requests on port 80. So anything that you do in PHP land needs to have an abstraction layer between your code and what Lambda is doing, or you just kind of do what Lambda expects. And it's all about calling Lambda's HTTP API rather than them calling you. So, as mentioned, layers are built on top of Amazon Linux 2. You zip them up. You push them to AWS in the layers area of the Lambda UI in the console or via API endpoint. And then you reference those layers, or somebody else's layers. In the case of Bref, they have layers pushed that are publicly available. So you can use those instead of your own. So now let's get into this custom runtime lifecycle. I told you it was kind of weird compared to just setting PHP-S or Nginx or FPM. So on Bootstrap, AWS will, in the case of not using a Docker container, it will look for a file, I believe it's /opt/bootstrap, and it will run that. And that's supposed to set things up, and if it's not successful, it'll return non-zero. If it's successful, then you'll set things up and start asking AWS on URL that's determined via an environment variable. Hey, what work do you have? And then you process the work, and then you send the result back, and then you clean up, and then you ask for more work. And that the amount of time between calling that initial Bootstrap file and asking for the initial set of work is your cold start, plus whatever Amazon does in the background. And then after that, the time between you requesting new work and Amazon handing something back to you, that part of the workflow is a warm start. And yes, that means that your HTTP request to ask for more work may time out, so make sure it doesn't time out. So again, there is a limit to how long your function can sit there and process. I think the default is a few seconds, and you can push that up to as many as 15 minutes. If you have a longer running job than that, you will need to split it up or not use Lambda. So, on Bootstrap, AWS initializes the runtime and pulls down whatever files are associated with a function, whatever layers, and then it sets a bunch of environment variables, and then calls your Bootstrap file, which should either get things ready to call to AWS and ask for work, or it should call an API endpoint saying, hey, I had a problem starting up. Once you've gotten to that point of a successful startup, then you ask AWS, hey, give me the next event, next invocation. It'll give you a response. You process that response, and then make a call back to AWS with the result of that processing. In certain cases, for example, the HTTP API stuff, whether that's through API Gateway or whether that's function URLs or the application load balancer, there is an expected format to that response for your response body and headers and status code. It is, again, not an HTTP message, but it's pretty straightforward. It's JSON. They no longer require you to do crazy base64 encoding of stuff. So while it's not just HTTP out of the box, it's not that hard to adapt things. And if you do have an issue running through your code, you can call an error request via that internal AWS API and say, hey, this didn't work. And at that point, AWS will close out that function and that instance and start a new one going forward. So one thing here is you can do cleanup. Of course, the clock keeps running, the billing keeps running. You can do cleanup after you send a response back to AWS, but before you ask for additional work. Just realize that that is build time, so you don't want to just sit there doing cleanup forever and not ask for another chunk of work. So your error logs do go into CloudWatch. You can actually see what's going on there. There are metrics that are visible on the function side as well, including function duration and that sort of thing. And there is a telemetry API that is available per function execution that you can hook into, operates over HTTP, that is out of scope for this talk. That is quite new. I believe that was actually announced at the most recent reInvent. But if you do have an error during the process of running the function, then you make another post call to this special Lambda API endpoint. So with all that said, that API is what you use whether you are running off of a Docker image or running off of a zip file. But if you want to, for example, not use something based on Amazon Linux 2, you can provide a Docker image, push it to a Docker registry. The easiest way of doing this is using Amazon's own Elastic Container Registry, or ECR. And then you can tell Lambda to use that rather than a uploaded zip file with the code in it. What that allows you to do is, again, use other base images and really treat your Lambda setup similar to what you would in a normal container. Now, caveat to that, again, is you still have to use the Lambda HTTP API to bootstrap, ask for work, etc. So you're still not going to be serving HTTP over this container. Now, that Lambda API is, they have the runtime interface client is what they call it, that implements that for you. And Amazon does have some base Docker images that include that client. The problem is there does not exist an official AWS runtime interface client that speaks PHP. And also, as an added bonus, the Node 1 does not work for Node 17 and above. So in this case, as you'll see in the demo portion of this presentation, we do have a little bit of code that interacts with that API directly, so we would just use that, continue to use that even in the container environment, and we're fine. Now, because that is kind of a weird API, Amazon has said, all right, well, we want you to be able to test this stuff locally in a containerized environment, pass events to it and get stuff back. So if you add the AWS runtime interface emulator, which is a binary, they have it for both x86 and ARM. If you add that runtime interface emulator binary and change your Docker command to be that temporarily, you fire up the runtime interface emulator. You tell it, okay, once you are set up, run my standard bootstrap file, which in this case can be anywhere in your container. Amazon doesn't care. They'll pass you the environment variables and leave you to do what you will. So yeah, the runtime interface emulator, it'll set up its own HTTP server and then call your bootstrap and go from there. And that'll allow you to test things locally. We're not going to demo that in this case because our setup is trivial enough that we'll just demo it in the cloud. But it is available, and Amazon does have that documented as to how to call that. You hit a single post endpoint, and you can pass an event body in there, potentially one of their test events. and see things process through. So with all of that, so my theory here, and again, this is not going to be exact on how AWS actually operates this, because they, for example, reserve the right to set up, to initialize Lambda instances ahead of load or whatever they want to do. But the idea here is when a request comes in, they check to see whether there's already a Lambda instance up and running. If there isn't, then go through the cold start process, run the bootstrap file, make sure that it gets all the way through and asks for work, then provide a response back with that unit of work, then wait for the response endpoint to be called, hand that back to whoever requested that event, and then keep the clock on billing until another request is made for the next unit of work. And potentially suspend animation on that Lambda instance until there is actually another event to process. So that's kind of the run through on what's more or less happening on the AWS side. It's great for event processing, a little bit weird for HTTP, but it's not that far out of line. So with that, we come to the demo portion of this presentation, in which I take a random string that I email or provide as an HTTP request, and then randomly capitalize it and hand it back in as mocking of a way as possible, which is fine because it's just mocking its creator. So first off, we're going to use Lambda for event processing in an asynchronous way. What I've done ahead of time is I set up a simple email service with MX records headed to the proper place, and email alias pushing to S3, because I did not want to wait during this presentation for MX records to propagate, etc. I also had to make sure that my AWS account was approved for sending emails. So all that's done. And I also created an IAM policy that I'll assign to Lambda saying, yes, you are allowed to read from S3. Yes, you are allowed to send emails to via SES. And yes, you are allowed to do the miscellaneous things that you do as a Lambda function. All of this is documented in the README on this repo, and I'll have a link to that repo at the end of this presentation. So what we'll do now is we'll go ahead and set up a Lambda function. I've also gone ahead and uploaded a Lambda layer with the PHP runtime already there. That was kind of, I shortcutted that by using the runtime compilation process that's built into Bref, because I did not want to reverse engineer that process, and Bref has done it amazingly. So it was a matter of run the Bref stuff, copy paste the runtime directory from there. Again, this is all in the README for this project, and then zip it up and push it to AWS. So let me hop over to Lambda here, and I'll show you where that was, but I'm not going to hit the upload button again because it's like 21 meg, and I don't want to take too many chances on conference Wi-Fi. So here we have SpongeBob base. This is that zip file. I've uploaded the layer a few times now, so we're up to version 5 here. It'll increment that if I uploaded it again. The thing that you'll do here if you're uploading a PHP layer is you'll specify which architecture. In this case, I had compiled it on my machine at home that was x86, so I would check the x86-64 box there, switch the runtime to custom on Amazon Linux 2, because your custom runtime is on Lambda or that now, and then upload the file. We'll back out of that because that file is already uploaded, and we'll skip to adding the function. So we'll hit create function here, alter from scratch, set our runtime to custom with our own bootstrap. Architecture is correct, permissions. We will use our own IAM role here with a couple of extra permissions so it can read from S3 and write to SES. And we'll go ahead and check the box for enabling a function URL and just leave the authentication open for that because I don't particularly want to deal with building AWS signatures to call my own silly endpoint. So I create this function. Now I specify a layer here that I had created earlier. Go to custom layers, find our single layer there, use the latest version, and hit add. Again, you can add these in whichever order makes sense for the project. Then, so we have a long list of events that we can use here. We're going to use S3. I already have the bucket created, so I'll specify that here. It defaults to all object create events, which is what we want. And you have to check the box to make sure that you know that you shouldn't call S3 stuff recursively and run up your AWS bill. So now we have a trigger for S3 into Lambda. The last thing we need to do is provide the code to actually run. So I'll go ahead and upload the zip file, and then we'll look at what I actually uploaded. So we want spongebot.zip. Save that. It's going to take a second to upload here. And now we have everything added in. So this is actually ready to go. I'm going to go ahead and send myself an email, and then it does take a few seconds to go through the email network and fire off the S3, saving to S3, and then firing off the Lambda event. So while we're waiting for that, I'll guide you through the code that I wrote to bootstrap this. So first off, I'm going to email So I'm going to hit the send button there. So while it's processing, the first thing we'll show is the bootstrap file for runtime, which is just a quick shell script that makes sure to call our actual bootstrap PHP file in a loop. Make sure that that stays running. From there, we have, I decided to not use any libraries here and just use file get contents because that's all I needed, and log some things out along the way. Because standard out does go into Lambda logs, this tends to be useful for running tests on the function. So one of the things I do there is I spit out environment variables, but I didn't want to show AWS access token secrets because those may have a few too many permissions. So as mentioned, we have a number of requests in here to various Lambda APIs, whether that is initialization fail, execution failure, getting the actual task, and then setting those headers up into a proper setup. This line right here is to properly instrument the runtime for AWS X-Ray so that you can do distributed tracing. And then we just pass that request payload back to whoever asked for it. Likewise, when we are done processing something, there's the submit call that just makes a request back to the AWS API. And again, these are all, that URL is determined via an environment variable that is passed to us when the function starts. So this is that bootstrap file. If we look at the index file, I have both the API-facing code that we'll see in a minute, as well as the SES processing code in here. And in the case of seeing an SES event, we actually grab the entire email object because the SES integration with Lambda does not include the email content. It just includes headers. So we grab that. We have Composer installed and included in that zip upload a MIME parser. So we pull the email body out of that, as well as the subject. We tack on a reply to the subject. And we send that back to whoever sent it to us. And then we randomly capitalize the entire message body using MB string to lower, MB string to upper, and then provide that as part of this SES API, which we're just using the AWS SES SDK for this because it's authenticated within Lambda, so you don't have to deal with any SMTP weirdness. So with that, this didn't take nearly as long as it took for me to explain this, but we now have this going on here. So we actually did round trip properly, and that was well within a minute to actually get that email passed to us. And the nice thing about pushing emails to S3 is we have the original email body if we wanted to use that for a test event for Lambda later on, which you can specify test events in the Lambda UI and see logs directly from them when you execute them. So that is our first example. The rest are going to go a little bit more quickly. So now that we've seen the code base, let's go ahead and add an API gateway and call the same thing over HTTP. So API gateway, we'll set this up for an HTTP API, not to be confused with the REST API. Don't click that button. We will use Lambda. We'll use our only Lambda function. And let's call that sponge bot. Go here. Drop the resource path. And hit the go button. This will spit out a URL that should be able to CNAME to as well. And if we go here, this output here is a Chrome extension I have. This would just be normal ugly JSON otherwise. So we've got instructions here that are annoyingly capitalized. So let me throw a query string parameter here. And hey, look, that works. And you might have noticed that this returned a little bit more quickly the second time than the first. That's because there's a difference between a warm start and a cold start. And I didn't go in and change the amount of RAM that was allocated. So this is running on 128 meg of RAM, which it doesn't actually need. I think it uses like 50 meg. And this did respond in like probably a millisecond on the server side, and most of the rest of it was latency because I was lazy and ran this in US East 1 rather than in London. So to give you an idea of when I say the request is a little bit different looking, this function checks to see whether there's a version in the HTTP bit, and we just use that to say, oh yeah, this is HTTP request. And if it is, then we've got query string parameters set out as their own JSON array. There's no need to parse those. And then we return JSON with a status code, and then the body that we just go ahead and JSON encode that, which then gets passed back as a string to the API with content type of text plain by our Bootstrap. So this is our request processor. It's not using an EPSR fun, but that gives you kind of an idea of the format of that inbound event from Lambda. So the next example that we're going to do is the exact same thing, but instead of going through the API gateway setup, now there are a few limitations on what I'm about to show you. For one, this doesn't work with containers. For two, you can't CNAME this. But if you don't need to CNAME it and you can just use a big long host name, then we can hop over to Lambda again without doing anything on the API gateway. And fortunately, they were consistent with the request payload format here. And if I hit the function URL here, then you'll notice the Lambda URL is a little bit different there. It's .on.aws. And we get the same response back. And if I do that, then we have the message pushed back as expected. So that there is consistency in the format between Lambda function URLs and API gateway. So I'm glad that at least those two teams at AWS actually talked. So with that, so we've got SpongeBob via API gateway and Docker. So in that case, realize we're running short on time here. We can create a function here using a container image. And can use this nice browse function here, grab the latest one. And I actually built this on my machine, so it's ARM64. We don't actually need to do anything with the execution role because we're just running this on HTTP. Create that function. And then we'll do the same thing with API gateway that we did before as soon as this loads. Go here, hit the go button there. And we'll notice once this gets set up that this takes a little bit longer to initialize, but it's not too bad. So same deal. You can look in the repo to see what all I had to change. The Bootstrap looks a little bit different. but there is a standard kind of Docker file in there. Finally, realistically, all the stuff that I showed you with the Bootstrap stuff, don't use that in production. Use Bref instead, because Matthew Napoli has spent a whole ton of time actually making Bref production ready and serving billions of Lambda invocations on it. So use that instead and find him because he's at this conference. To give you an idea of how much easier that is, this will take a minute, but it's using serverless framework, which, yes, it's a node thing. You'll have to run npm. I ran it ahead of time because I don't want to sit here waiting for npm to install. But this uses CloudFormation and API gateway and such to build out Lambda executions there, and you can actually use standard kind of PHP FPM setup within this, or you can just respond to events directly as well. So once this runs, we will get an API gateway URL back. We'll throw that in the browser and see that that does, in fact, work. The branch I'm on right now is using Bref 1.7. Bref 2 is currently in beta. Played with it yesterday, and it cleans up the config file format a bit and does a whole lot of under-the-hood improvements. So I figure that'll be available soon, but you can't go wrong here. So with that, suppose we have a couple of minutes for questions, and while I'm taking questions, once this actually finishes doing CloudFormation things, then I'll show you that it has actually worked.
Okay, there was a question on Discord that came through. So regarding the custom runtime Lambda, what's the support level for custom runtimes in CloudFormation? Is it all doable in an infrastructure as code setup?
So short answer is yes, because the way that Bref works is it's using serverless framework, which is using CloudFormation.
And any other questions from the room? Okay so far.
And so that did finish running. I go there. And again, we see our prompt for providing a message there. And again, all this code is available on GitHub. The last slide in this presentation, namely here, has that information on it. So I suppose that is all I have. Thank you so much for your time and attention. And if you have questions about this presentation, feel free to find me through the rest of the conference. If you have questions about Bref, then you should find the person who built most of it.
Thank you very much, Ian.